All right, question 20.32 simply asks us to provide the reagents for these transformations. So the first one, we're going from benzoic acid, and we want to make this secondary alcohol here. Well, this is one of those reactions, or excuse me, syntheses, where we're going to have to use one of the reactions that we learned in this chapter. Namely, just in terms of retrosynthesis, if we could make the acid chloride, and I think we all know how to do that by now, if we could make the acid chloride, we can just add the ethyl group, right? This is an ethyl group, and we can add that using a Gilman reagent, which is ethyl cuprate, right? The lithium ethyl cuprate. So again, this is a Gilman reaction, or we call it a Gilman reagent. And so again, I think everybody knows how to get from the carboxylic acid, benzoic acid, to the acid chloride. So what do we have to do? We have to take our carboxylic acid. We're going to treat it with thionyl chloride. That will give us our desired acid chloride. And then we're going to treat that with our Gilman reagent. So the ethyl cuprate, like that. And there we go. We end up adding one ethyl group to the acid chloride, to the electrophilic carbon. And there we have it. We have our secondary alcohol. In 20.32b, now this one is a little trickier in terms of retrosynthesis. But if we think about breaking this bond right here in our retrosynthesis, what if we had this compound? This is called benzyl alcohol. So this is called benzyl alcohol. And what if we just acetylated that using acetyl chloride, right? Or acetyl chloride, whatever you want to call it. If we use this in pyridine, right, plus benzyl alcohol, that would give us the desired compound. All right. So how do we get from bromobenzene to benzyl alcohol? Well, what are we going to do? We're going to have to add a carbon, right? Because we're starting it with 6 carbons, and then we need 7 carbons in the next compound. So in order to do that, why don't we use the Grignard strategy, which is where we use magnesium in diethyl ether. Then we treat the reaction mixture with CO2, and then we treat it with acid, aqueous acid, and that will give us benzoic acid. So there we go. This is benzoic acid, and we can reduce benzoic acid to the primary alcohol, benzyl alcohol, either using lithium aluminum hydride or by using boron and THF. Either way is perfectly reasonable. So why don't we just choose, I don't know, let's choose lithium aluminum hydride followed by aqueous acid, and that gives us benzyl alcohol. And then all we have to do is to treat that with acetyl chloride, okay, plus pyridine, and there you have it. All right, so somebody asked a question. For A, I used a hindered. So for A. Oh, I see what you're saying. Okay, so what Skylar is saying that for A, yeah, for A, let me see. I think I know what you're saying. You're saying that you treat it with okay. I don't know if that would work in A. Yeah. Yeah, just let me think about that for a second. I don't think that'll work. Okay, because the only time that we used um, the tri-butoxy aluminum hydride is when we reduced an acid chloride. You see what I'm saying? Yeah, we have no way. Okay. Yeah, we have. Okay, good. Thanks for answering. Yeah, we have no way to go from a carboxylic acid directly to an aldehyde. If you want to make an aldehyde, we could make it from an acid chloride. So in that case, you could take this compound, right? Okay, good. And you could take that and you could treat it with lithium tri-butoxy, aluminum hydride, and then treat that with water in the end. And that would give you benzaldehyde, right? And if you had benzaldehyde, in that case, yeah, you could treat it with ethyl magnesium bromide. Yes, that would work. Followed by treatment with aqueous acid, or in our book, it always says H2O. Yeah, does that help? Sorry, I think there's a bit of a delay in what I'm reading on my Microsoft Teams, but does that help a little bit? And when I say a little bit of a delay, I mean there's a long delay. Okay, good. All right. Well, let's take a look at one more problem from chapter 20. This will be the last problem we'll take a look at, unless anybody has a specific problem they want me to look at, which I'd be happy to do. But I wanted to take a look at 20.32 C, and I don't think this is a simple problem. It's definitely a reasonable problem, but I don't think it's simple. So we're going to start with this compound. Remember, this is called benzonitrile. You replace oic acid with onitrile, so benzonitrile. And then we're going to make this interesting compound here, where we have an oxygen here. We have a geminal dimethyl here, and then we have an acetyl group on there. Well, I don't think it's much of a stretch to do the last step because we just looked at an acetylation a few minutes ago. So if we had this alcohol, if we had that tertiary alcohol, all we'd excuse me, all we'd have to do is treat it with acetyl chloride and pyridine. So that's fine. But then the question becomes, like, how do I get from here to here, right? And also, I'm adding 2 methyl groups to the molecule, right? You're starting out with a total of 7 carbons here, and you're ending up with 7, 8, 9, right? Oops, 9 carbon. So we need to add these 2 methyl groups. So, well, what method do we have for adding 2 methyl groups, right? If we could make the acid chloride, and I'm going to do another retrosynthesis step here. If we could make this acid chloride, so just 1 carbon, right? Then all we'd have to do is treat it with excess methyl magnesium bromide, followed by treatment with water, and then that would give us that desired tertiary alcohol. So then it gets a lot simpler, right? If we want to go from the nitrile to the acid chloride, I mean, we all know how to convert the nitrile into a carboxylic acid. We treat it with aqueous acid, we heat it up, right? So we just heat it up like that, and that's going to convert this into the carboxylic acid like that. Right, then we can treat it with thionyl chloride, and we make the acid chloride. So this is benzoyl chloride. Okay, then we're going to treat it with excess methyl magnesium bromide, followed by treatment with water. That's going to give us the tertiary alcohol that we want. Let's write that down. And then in the last step, we're going to treat it with acetyl chloride and pyridine, like that. And there you go. So overall, how many steps is this? Let's see. It's 1, 2, 3, 4, only 5 steps. It's not that bad. It's more about making the kind of the retrosynthesis is key and understanding how you might put this together, right? It's not, maybe not super evident, but anytime you see an acetyl group, you know that you're going to have to do an acetylation as your last step. So acetyl chloride, this compound, I'll draw it in green here. You can assume that you would always have that as a reagent. It's a very common reagent in organic chemistry. It's a liquid at room temperature, cheap. So yeah, there you go.